Usually when we talk about a medical diagnosis, there's, this expectation of clinical precision.
Right, it's very binary.
Exactly. You break your arm, the x-ray shows a jagged white line, and the doctor just points and says, well, there it is. Broken or not broken.
It is comforting, I think. We really like human biology to be visible, categorized, and just neatly boxed into cause and effect.
We do. But today, we are throwing that comfort totally out the window. Welcome to today's deep dive, everyone. We are looking at Claudia Tange-Mirk's book, Physics of Cancer, Volume 2. And we're going to prove that cancer isn't just like a genetic typo.
No, it is a biomechanical invasion force.
Yeah. And our mission today is to decode the physics of how it actually moves. Because for decades, oncology has treated cancer almost exclusively as a genetic disease, right? We look for the mutations, the errors in the cellular blueprint.
Which is important, obviously.
Right, of course. But for you listening, whether you're a medical student prepping for boards, a young professional in the clinic, or just someone who is insanely curious about human biology, we are taking a totally different path today. We are looking at the bricks and mortar.
And what's fascinating here is that while genetics load the gun, it's the physical forces, the cellular mechanics, and the structural barriers that actually pull the trigger on metastasis.
Right.
If we want to understand how a localized tumor becomes a systemic life-threatening disease, we have to understand the physical rules of the tumor microenvironment.
And this biomechanical perspective, it isn't just theory, is it?
Not at all. It
Yeah.
is absolutely crucial for the next generation of diagnostics and personalized therapies. I mean, you cannot stop a moving target if you don't understand the engine driving it.
Okay, let's unpack this, because before a cancer cell can even think about spreading to another organ, it has to physically move. It has to navigate its own internal physical limitations. And the source material points us to two critical structures inside the cell, the microtubules and the nucleus. Let's start with the engine. What exactly is physically pushing this rogue cell forward?
Well, it's the microtubules.
Yeah.
And you have to stop picturing them as static scaffolding, like the steel beams of a building.
Right, that's the default image we all have from Bio 101.
Yeah, but they are the actual structural and migratory engine. If you zoom in on them, they are these hollow cylinders, roughly 25 nanometers in diameter.
Okay.
And they are built from tiny molecular bricks, specifically alpha and beta tubulin heterodimers.
Alpha and beta tubulin.
Right. And these bricks bind head to tail to form a long string called a protofilament. Then exactly 13 of these protofilaments arrange themselves side by side to form a closed tube.
So it's like a bundle of 13 tiny molecular cables forming a microscopic pipe.
Exactly. And this pipe has a distinct polarity, a plus end and a minus end. But the defining characteristic, the mechanism that actually generates the force for cell motility, is a phenomenon called dynamic instability.
Dynamic instability. I mean, that sounds like an oxymoron. How can a structural engine be unstable by design? If the engine in my car was dynamically unstable, I'd never make it out of the driveway.
It is entirely counterintuitive. Unlike standard polymers that just grow until they run out of building blocks, microtubules experience random, alternating periods of steady growth and then violent, rapid shrinkage.
Wait, they shrink?
Yeah, they add tubulin bricks, growing longer and longer until a sudden catastrophe occurs.
A catastrophe, like that's the actual term.
That is the scientific term, yeah. The tube rapidly unpeels and just falls apart. But then just as suddenly, a rescue event happens. The disassembly stops, and it starts building itself back up again.
Wait, so the engine is constantly exploding and rebuilding itself. How on earth is that controlled?
It's controlled by a chemical timing mechanism called GTP hydrolysis.
Okay, explain that.
So for a tubulin brick to join the microtubule, it has to be bound to a molecule called GTP. Once it's locked into the tube structure, that GTP slowly converts or hydrolyzes into a different molecule, GDP.
So it's a chemical reaction happening inside the structure after it's built.
Yes, exactly.
Yeah.
And you can think of that hydrolysis like a burning fuse. As long as the microtubule is growing fast enough, adding new GTP tubulin bricks to the tip, it maintains a stable cap. The fuse hasn't reached the end.
Got it. But if the growth slows down...
Right. If it slows down and the burning fuse of hydrolysis catches up to the very tip of the microtubule,
the cap disappears.
and that's your catastrophe. Without the GTP cap, the structural tension changes. The protofilaments curve outward like a peeling banana, and the whole tube rapidly breaks down.
Wow.
The cell uses this constant, rapid probing, growing out, collapsing, growing in a new direction, to physically push its membrane forward and navigate its environment.
That is wild. But here's where it gets really interesting, Franny. if the microtubules are this dynamic, shape-shifting engine pushing the cell forward, I can't help but look at the
The
cargo.
nucleus.
Yes. If the cell is a car and the microtubules are the engine, isn't the nucleus just a massive, unyielding piece of rigid luggage? I mean, it takes up a huge portion of the cell, and it's full of tightly packed DNA. It seems like it would never fit through the doors of the dense tissue matrix outside.
That analogy is spot on, actually. And it highlights a major physical bottleneck in cancer metastasis. The nucleus is the ultimate physical barrier to three-dimensional cell migration.
Because it's so big.
It is the largest, stiffest, and most inflexible organelle in the cell. When a cancer cell tries to squeeze through the dense, tangled meshwork of the surrounding tissue, the flexible outer membrane makes it through, the cytoplasm makes it through.
But the luggage gets stuck.
The nucleus gets stuck, yes.
So there has to be a physical limit. How small of a hole can this luggage be shoved through before something just breaks?
The physical limit is remarkably strict. The nucleus can only deform up to about 10% of its cross-section.
10%.
It's just 10%. For a typical cancer cell, the absolute physical limit for squeezing through a pore in the tissue matrix is a cross-sectional area of roughly 7 square micrometers.
7 square micrometers. I mean, that's microscopic, obviously, but context is everything here. How does that compare to a cell that is actually supposed to move around the body?
Well, let's compare it to a T lymphocyte. That's an immune cell whose entire job description involves patrolling through dense tissues to hunt infections.
Right, they move everywhere.
Exactly. Its physical limit is roughly 4 square micrometers.
Oh, wow. So they can squeeze through much smaller spaces.
Yes. Immune cells are evolutionarily engineered to be incredibly squishy. Cancer cells, particularly those arising from epithelial tissues like the breast or colon, they are not. They are built to sit still.
Right.
So if a migrating cancer cell is forced through a pore smaller than that 7 square micrometer limit, the mechanical stress becomes catastrophic.
What actually happens? Does the cell just get stuck like Winnie the Pooh in the honey tree?
It's worse than that. The nuclear envelope literally ruptures under the mechanical pressure.
You mean it breaks open?
The physical casing of the nucleus tears open, yes.
Oh, wow. So the luggage rips open and the DNA just spills out into the cell.
Essentially, yes.
Yeah.
And this is a massive crisis for the cell. It completely stalls the migration. The cell has to immediately halt, scramble its DNA repair machinery, and try to patch the envelope.
That sounds fatal.
It often is.
No.
If the mechanical tear is too severe, or if the DNA takes too much damage during the rupture, it triggers apoptosis, programmed cell death.
Wow.
The cell essentially kills itself because it tried to squeeze through a door that was too small.
So let's say the cell survives dragging its oversized luggage to the very edge of the primary tumor, hoping it doesn't tear itself apart. It can't just float away into the void. What exactly is it stepping into?
It is stepping into the extracellular matrix, the ECM. This is the non-cellular terrain of the body. It's the physical scaffolding that holds our organs together. And the primary structural component of this scaffolding is a protein called collagen type I.
Right, collagen.
Yeah, and in healthy normal tissue, these collagen fibers are relaxed. They're somewhat curly, pliable, and randomly oriented in all directions.
So it's like a tangled, dense, chaotic forest. But the source text explains that the tumor actively changes this terrain through a process called desmoplasia, right?
Yes, primary tumors are not passive lumps of rogue cells. They are highly active, manipulative environments. They release chemical signals that recruit healthy cells, particularly fibroblasts, and corrupt them into reactive fibroblasts.
Reactive fibroblasts.
Exactly. These reactive cells go into construction overdrive. They secrete massive amounts of new collagen, and more importantly, they secrete enzymes that cross-link these fibers together. This is desmoplasia.
So what does that actually do to the physical structure of the forest, so to speak?
Those normally curved, relaxed collagen fibers thicken. They pull taut, they lengthen, and they completely linearize.
Linearize, meaning they straighten out.
Yeah.
It's like taking that tangled, unnavigable forest, chopping down all the vines, and paving a multi-lane superhighway.
That's a great way to look at it.
And these highways are oriented specifically to point away from the tumor, right?
Yeah.
Giving the cancer cells a direct physical track to ride on and escape.
That is a highly accurate visualization. These straightened, stiffened collagen bundles can span several micrometers, radiating perfectly outward from the primary tumor into the surrounding healthy tissue.
That's honestly terrifying.
It is. The cancer cells physically attach to these linear tracks and use them to migrate out.
But wait, this brings up a massive contradiction. Anyone prepping for clinical boards knows this. You check for breast cancer by feeling for hard lumps, right? Palpation.
Yes.
The tumors themselves are physically stiffer than the healthy tissue around them, but the sources highlight a stiffness paradox. If the tumor is a hard, rigid mass, why does the literature say the metastatic cells themselves are soft?
It is one of the most brilliant mechanical paradoxes in oncology, honestly. At the macroscopic level, what a doctor feels with their hands, the primary tumor is undeniably stiff.
Right, the lump.
The desmoplasia, the excess tightly wound collagen, the increased fluid pressure inside the mass, it all creates a very rigid lump.
But the cells are soft.
Yes, when biophysicists isolate the highly invasive metastatic cancer cells from that mass, they find that these individual rogue cells are significantly softer and more deformable than the non-invasive cells left behind.
Okay, I understand needing to be squishy to fit that giant nucleus through the 7-micrometer pores. We covered that. But if the cell is completely soft, how does it move? You can't drive a car on sheer ice with bald tires. You need grip. You need traction.
And that is exactly the tension of the paradox. To physically drag itself along that collagen highway, the cell has to generate massive pulling forces. If it's too soft, it just slopes.
Right, it wouldn't go anywhere.
You can't pull against the stiff matrix. So the solution is active mechanical adaptation.
Active adaptation.
Yeah. An invasive cancer cell is essentially a shapeshifter. Depending on the physical stiffness of the substrate it is touching, it can rapidly rearrange its internal actin cytoskeleton.
Oh, wow.
It stiffens up just enough to generate the traction forces needed to grip the road, while keeping its overall body deformable enough to squeeze through the tight spaces.
It constantly calibrates its own squishiness based on the road conditions. I mean, that is incredible engineering. But let me put on my clinician hat for a second here.
Okay.
How on earth are we actually measuring this? We are talking about the mechanical stiffness of microscopic cells and individual collagen fibers. If I am a researcher or a doctor, how am I quantifying microscopic squishiness?
The text highlights two major technologies, and they operate on vastly different scales. In the clinical setting, we rely on magnetic resonance elastography, or MRE. You can think of it as palpation by imaging.
Palpation by imaging, like the MRI machine is something reaching in and feeling the tissue?
Mechanically, yes. An actuator is placed against the patient's skin, usually over the liver or breast, and it generates low-frequency shear waves, literal physical vibrations.
Like dropping a pebble into a pond and watching the ripples?
Exactly like that. These ripples, these shear waves, propagate through the patient's internal organs, and the MRI scanner takes incredibly fast images of these propagating waves in real time.
Okay, so you can see the ripples moving.
Yes, and by analyzing the wavelength and the speed of those ripples, the software calculates the complex shear modulus, the exact stiffness of the tissue.
Wow.
A stiff tumor transmits a shear wave very differently than healthy, soft liver tissue. It allows doctors to map the mechanical rigidity of an entire organ without making a single incision.
Okay, I totally buy that for the macro scale. That makes
Wow.
sense. But what about the micro scale? When researchers figured out that individual cancer cells were softer, they definitely weren't putting a single cell into a full-body MRI.
No, definitely not. For the cellular level, biophysicists use a technique called active microheology. And the gold standard tool here is something called optical tweezers.
Wait, hold on. Optical
Okay.
tweezers. The text mentions highly focused laser beams hitting dielectric particles, causing momentum changes through refraction. I'll be honest, you're losing me. That sounds like a heavy physics textbook. How does a beam of light physically hold and squeeze a piece of human tissue?
It's a fair pushback. The physics are really dense there.
Huh.
Let's simplify the mechanism. Have you ever taken a hairdryer, pointed it straight up, and floated a ping pong ball in the stream of air?
Yeah, of course. The ball just bobs perfectly in the center of the invisible airstream.
Right. The stream of air is pushing up, but because the air curves around the shape of the ball, it creates a pocket of pressure that traps the ball in the exact center of the column.
Okay, I can picture that.
Light has momentum, just like that stream of air. In an optical tweezer, researchers take a microscopic glass bead and drop it into a living tumor sample. Then, they fire a highly focused laser beam at the bead.
A laser beam.
Yes. And as the billions of photons stream through and bend around the glass bead, they exert tiny, precise physical forces. Just like the hairdryer, the light creates a pressure gradient that traps the glass bead perfectly in the center of the laser beam.
So you have a physical glass bead locked in a microscopic beam of light. How does that measure stiffness?
But once the bead is trapped, the researcher moves the laser. They use the laser to physically drag the bead back and forth through the living cell or the collagen matrix.
Oh, I see.
By measuring exactly how much the tissue resists that movement, how hard the tissue fights back against the bead. They can calculate the precise viscoelastic properties of the environment on a nanometer scale.
That is mind-blowing. Okay, so what does this all mean? Let's take stock for a second. We have a shape-shifting cancer cell powered by an exploding and rebuilding microtubule engine.
Right.
It's dragging a stubborn, fragile nucleus along a paved collagen superhighway. But it's not doing this alone, is it? We touched on fibroblasts earlier, but there's an entire ecosystem at play here.
Yes. The tumor microenvironment relies on accomplices. The cancer cell actively corrupts healthy cells to do the heavy lifting. We mentioned the cancer-associated fibroblasts, or CFs.
Yeah, the road builders.
Right. They don't just secrete the collagen for the superhighway. They physically pull on it, and they lay down a specific protein called fibronectin.
Fibronectin, okay.
They align this fibronectin parallel to the collagen, creating a highly directional chemical and physical track that forces the cancer cell to migrate outward.
Okay, I can understand fibroblasts being hijacked to build roads, but I have to push back hard on another cell type mentioned in the sources.
Let's hear it.
From day one of med school, biology classes teach us that the immune system is the ultimate defender. Macrophages are the body's garbage collectors. They hunt down rogue cells and devour them.
They do, usually.
But looking at Merck's text, it claims that macrophages are actively helping the tumor metastasize?
It is arguably the darkest irony of tumor biology. Tumor-associated macrophages, or TAMs, are routinely reprogrammed by the tumor.
Reprogram?
Yes, and their physical interaction with cancer cells forms the basis of one of the most lethal structures in all of oncology, the TMM triad.
TMM, the tumor microenvironment of metastasis. What exactly is this triad, and how does a macrophage fit into it?
The triad is a highly specific, temporary assembly of 3 distinct cells. It requires an endothelial cell, which is the physical cell lining the wall of the blood vessel.
Okay, that's one.
It requires a macrophage, that's 2, and it requires a cancer cell. But specifically, a cancer cell that is overexpressing a protein called MinA-INV.
So these 3 cells physically bump into each other right at the boundary of the blood vessel. You have the vessel wall, the cancer cell trying to get in, and the macrophage. What triggers the breach?
Physical contact.
Just touch.
Just touching. When the corrupted macrophage comes into direct physical contact with the MinA-INV expressing cancer cell, it acts like a mechanical switch. That physical bump triggers a massive chemical signaling cascade inside the cancer cell, specifically activating a master regulatory protein called RhoOA.
Okay, I am stuck on this macrophage connection. Are you telling me that by simply touching the cancer cell, the macrophage is accidentally handing it the keys to the bloodstream?
That's exactly what's happening.
How does a physical bump and this ROA protein translate to a breach in the vessel wall?
That physical touch changes the cancer cell's architecture. RhoOA is a master regulator of the cell's actin cytoskeleton. When the macrophage triggers RhoOA, it commands the cancer cell to rapidly assemble what are called invatopodia.
Invatopodia?
Yes. Think of invatopodia as aggressive, microscopic battering rams pushing out from the cell membrane. But they aren't just blunt physical spikes, so they are highly concentrated with metalloproteinases.
Which are enzymes, right?
Powerful enzymes that literally chew up and dissolve structural proteins.
So the macrophage touches the cancer cell grows these enzymatic spikes, and then what?
The invatopodia melt through the basement membrane and physically pry apart the endothelial cells lining the blood vessel. They create a temporary doorway. The cancer cell then slips through this doorway and plunges into the bloodstream. This process is called intravasation. And without the macrophage making that physical contact and triggering the invatopodia, the cancer cell simply cannot breach the wall.
That is terrifyingly efficient. So the cancer cell has broken into the bloodstream. And by the way, surviving the bloodstream is a whole other biophysical nightmare.
It really is.
The sheer fluid stress of the blood flow can rip a cell to shreds, which is why circulating tumor cells often coat themselves in a protective shield of platelets just to survive the tumbling.
Exactly. They have to hide.
But eventually it has to land. It doesn't just crash blindly into a new organ, does it?
No. A metastatic cancer cell cannot survive in a hostile, unprimed foreign tissue. If it just randomly dropped into healthy lung tissue, it would likely die.
It needs a safe harbor.
It needs a hospitable, mechanically compliant environment. So long before the circulating cancer cell ever arrives, the primary tumor sends out scouts to prepare the terrain.
Scouts. It's like a highly coordinated VIP traveling. You don't just have the VIP show up to a random hotel in a new city. You send an advance team weeks ahead of time to unlock all the doors, Adjust the thermostat, bribe the staff, and make sure the room is perfectly prepped before the VIP ever steps foot in the lobby.
As the exact mechanism. The advanced team in this context takes the form of tumor extracellular vesicles, primarily exosomes. Yeah,
Exosomes.
these are incredibly tiny, membrane-bound packets loaded with specific proteins, lipids, and microRNAs. The primary tumor constantly secretes millions of these exosomes into the bloodstream.
And how do these microscopic packets actually prep the hotel room in, say, the liver or the lungs?
They physically interact with the endothelial cells of the blood vessels in those distant organs. The exosomes actively induce vascular leakiness. They make the blood vessels in the lung more permeable, literally opening the doors. Furthermore, they exit the vessels and interact with the resident fibroblasts in that distant organ. They trigger them to start altering the local extracellular matrix, laying down new collagen to mirror the stiffened desmoplastic environment of the original primary tumor.
They're terraforming the distant organ.
Precisely. They establish what oncology calls the pre-metastatic niche. They guarantee that when the circulating tumor cell finally drops out of the bloodstream, the physical tension and biochemical makeup of the new environment is already perfectly primed for a secondary tumor to take root and flourish.
It completely reframes how you look at the disease. It's not just a rogue cell dividing out of control. It is a highly coordinated biomechanical invasion.
It really is.
We started by looking at the dynamic instability of the microtubules, the fuse-burning engine driving the cell forward. We looked at the massive, fragile nucleus that has to deform perfectly to squeeze through a tiny 7-square micrometer pore without tearing itself apart.
Which is a huge physical hurdle.
Yeah, and we saw how hijacked fibroblasts pave stiffened collagen highways, and how the cancer cells actively shapeshift, softening up to squeeze and stiffening up to grip the road.
And we saw how the tumor weaponizes the immune system, using corrupted macrophages in the TMEM triad to literally punch a hole into the bloodstream, while millions of exosomes fly ahead to terraform the landing zone.
It is a masterclass in exploiting biophysics. Now, before we go, for you medical students and curious learners out there listening to this, forget the flashcards and the genetics for just a second. If you want an insider secret for understanding metastasis, the one concept you absolutely need to lock into your memory is the TMEM triad.
Absolutely.
Let's do a quick mental review. Next time you look at a tissue slide, remember the 3 players.
The macrophage, the endothelial cell, and the MEN-I-NV cancer cell.
Right. It is their physical contact that triggers ROA, forming the invadipodia that melt the vessel wall. Commit the mechanics of that doorway to memory. Now, as we wrap up this deep dive into the physical reality of cancer, I want to hand it over to my co-host for a final thought. We spent the entire show looking at how cancer moves. Where does this leave us for stopping it?
Well, if we connect this to the bigger picture, if cancer cell migration relies so heavily on the physical stiffness of the matrix, the dynamic instability of the microtubule engine, and the mechanical signaling of macrophages, could the future of oncology involve purely biomechanical therapies?
Biomechanical therapy?
Yeah. What if, instead of trying to selectively poison rogue genetic cells, which always carries massive systemic side effects, we simply alter the physical tension of the tissue?
Oh, wow.
What if we use drugs to relax the collagen superhighways? Or mechanically freeze the actin cytoskeleton so the cell can't generate traction? What if we trap the cancer exactly where it is, rendering it a localized harmless lump simply because it physically cannot move? It forces us to ask, is the ultimate cure for cancer going to come from a geneticist or from a mechanical engineer?